Hello everyone and welcome to this lecture. In this lecture, we will talk about one of the most celebrated result in recent times in theoretical computer science. Okay, the result is about sensitivity conjecture, which is now a theorem. It was proven in 2019 by Hao Huang, but before that it was open for last 30 years, and there is one other reason why this is one of the most beautiful proof and very well celebrated. The reason is the proof given by Hao Huang is very simple, very elegant, and we have already seen in this course that that Cauchy-Intel's theorem help us in many times. Hao Huang had actually made a very beautiful use of Cauchy-Intel's theorem, and then how the eigenvalues are related with the degrees of graphs and all. In fact, the computer scientist Scott Aronson has given a very beautiful quote on this proof that it's hard to imagine that even God can think about a simpler proof than given by Hao Huang. Okay, so let us see what this conjecture is about, which is now a theorem, and this conjecture is actually about the sensitivity of Boolean functions. Okay, and so let us go with what this conjecture is, and but before that I need to have some notations, and then I will talk about sensitivity, and then there is one more concept of Boolean block sensitivity. Okay, and then we will see how they are related. This conjecture is about actually the relationship of these two sensitivities. Okay, so let us go ahead with defining what sensitivity means. Okay, so before that I need a notation. Okay, so notation. Okay, very good. Okay, so we will be dealing with Boolean functions. Okay, so Boolean functions are what? A function which takes Boolean strings as input and output either 0 or 1. Suppose we have a binary string. Suppose let x be a binary string. Okay, so suppose this x, let me write it x1, x2 up to xn, and each of this xi is either 0 or 1. So it is a binary string. Okay, binary string. Okay, and suppose S is your some subset of numbers from 1 to n. Okay, by xs we denote binary string is by we denote the binary string obtained from x by flipping all the entries indices by indices in S, right? All the entries whose indices are in S. Okay, so basically suppose if your string was this, okay, so suppose 0 0 1 0, okay, and your S was suppose 1 and maybe 2 and 3, okay, in that case XS will be what? XS will be this 0 1 0 0. Okay, so these two will be flipped. Okay, very simple one. Now let us go to the definition of sensitivity of a Boolean function. Okay, so sensitivity. Okay, very good. So what are Boolean functions? So Boolean functions are functions, okay, which takes input as some string of length n. This is a binary string because it's a Boolean function. Okay, and the output is either 0 or 1. So we are like AND function or function, right? So these are all our Boolean functions. Okay, now in order to define sensitivity of f, right, first we will tell what we mean by local sensitivity of f on some input x. Okay, so suppose x is some input. Suppose x is some some input, okay. So X is some binary string, basically a binary string, right? Binary string, okay. Some binary string is some input, okay. Then what is first, we will denote a local sensitivity, sorry, the spelling is sensitivity of X in F, okay. So local sensitivity of X, okay. It is defined as this. So let me first just denote it by this notation, okay. So local sensitivity of X with respect to our function f(x), this, okay. So it is actually the number of indices I such that the output flips, okay. The output flips, that means f(x) is not equal to fi, okay. So like this, okay. So this is local sensitivity. So number of indices, we will check the indices, and the number of indices where such things happen by toggling index, the output actually toggles, okay, basically flips, okay. Very good. So now sensitivity of function is this. Now sensitivity of function, sensitivity of f is nothing but the maximum of all local sensitivities. So maximum over all inputs and then their local sensitivities, okay. So let us see one example. So suppose let us take a case of AND function, okay. So AND function, okay. So AND function is what? So your input is suppose this string up to xn, okay, and this tells this, right, x1 and x2 and dot and xn, okay. Now let us see two strings and then let us calculate its first local sensitivity and then try to find what will be the sensitivity of function, okay, and function, okay. So suppose your one input is this, okay. So all one vector, so suppose 1 1 1, okay. Suppose I denote it by this, okay. What will be the local sensitivity of this? What will be the local sensitivity of, basically sensitivity of this? What will be? Okay. You see that f(x) for this input is 1, right? All this AND function, the AND of all the ones will give you 1, right? If you flip any entry of this input, the answer will be changing, okay. So the local sensitivity is nothing but n here, right? So there will be n indices, you can basically flip any entry, the answer will be changed, okay. Very good. And let us take another vector. So suppose this is 0 vector where all entries are zeros, okay. What will be the local sensitivity of 0, okay? The local sensitivity of 0 is nothing but what? 0. Why? Because just changing, you pick any index, right? You flip it, the answer will still be 0, right? Because the answer for this is 0. By changing any entry, the answer will still be 0. So the local sensitivity of this is 0. Okay, very good. Now what about the sensitivity of AND function? Okay, what about the sensitivity of f? This is the maximum over all the local sensitivities, right? Maximum over all local sensitivity. What could be the maximum one? The maximum could be n, and which is in fact for this all one basically binary vector. Okay, so this will be equals to n. Sorry. Very good. This will be equal to n. Okay. Now let us come to another concept that we called block sensitivities. Okay. So block sensitivity of a function, Boolean function. Okay. Function. So again, first we will define local block sensitivity of an input X, okay, and then we will define block sensitivity of function, okay. So local block sensitivity of an input. So local block sensitivity of X or input X of an input X. X is your any binary string, okay, of length n. Okay, very good. So how this is defined? Okay, this is the maximum number of disjoint blocks, B1, B2 up to Bk, such that for any Bi, for each Bi, okay, if you basically flip all the entries in Bi, the output change. So Fx is not equals to FxBi. Okay, remember this notation this X to the Bi we have already defined here, this notation. Okay, very good, very good. Okay, now remember this these blocks need not to be continuous. The only thing is these blocks are disjoint, and in each block these indices need not to be continuous, to be precise. Okay, very good. Okay, so and now let us see one example of it. Let us take again maybe the local block sensitivity with respect to AND function. Again, take AND function. Okay, what do you think? So and let us take two string again. So one is this one. Okay, what will be the local block sensitivity of all one? What will be the block sensitivity? Okay, if you see that by default, if you take each of these indices as a block, so suppose this is a block, this is a block, this is a block, right? By changing any block, so the block is of size just 1, right? By changing it, the output changes. So the local block sensitivity, so let us define it by Bs, denoted by Bs of this vector is nothing but n, right? Because there are n such blocks. Okay, very good. Now what about this vector? This vector or string. Okay, so what will be the local block sensitivity of 0 or 0 vector? Okay, now remember the local sensitivity, we have seen that it's a 0, but what about the local block sensitivity? If you see it carefully, that we need to flip all these entries, right? So we have to take a block of all the entries and flip them all together, then only the output will change. Okay, so the local block sensitivity of this string is nothing but 1. Okay, and this happens for when you take block, or maybe basically all the entries, and the block consists of those entries. Okay, very good, very good. Now let us define what we mean by block sensitivity of function. So block sensitivity of a function, Boolean function. Okay, very good. Okay, so very good. It's like we have defined for this sensitivity. Okay, so the block sensitivity is nothing but block sensitivity. So I will denote it by this. Okay, of function is nothing but the maximum over all local block sensitivity. So maximum of over all the inputs, and then block sensitivity of Okay, very good. So what will be the block sensitivity of AND function? Again, it could be again at most n, right? So the block sensitivity is here. So block sensitivity for AND function, basically let me write AND function is nothing but n here. Very good. Now comes the interesting question, the relation between block sensitivity and sensitivity. Okay. One obvious thing is that the block sensitivity is at least the sensitivity. Why it is so? Why it is so? Okay. If you see it carefully, the definitions, right? The local block sensitivity, the local block sensitivity is always greater or equal to, is always greater or equals to the local sensitivity, the local on any input, okay, or local sensitivity on any input, okay, on any x, I would say on any x. This implies thus the block sensitivity, okay, so let me write it, thus the block sensitivity of a function is always greater or equal to the sensitivity of a function. Okay, so we have just seen the example here, the block sensitivity, in fact here it is coming out to be equal. The interesting question is, for what kind of function? Can you give an example of function where block sensitivity is strictly greater than the sensitivity of function? Okay, so this is one DIY for you. Okay, now comes a very beautiful conjecture on these two sensitivities, the block sensitivity and sensitivity of a function, and this conjecture was given by Nissan and Sejedi in 1989. It says that these two sensitivities are polynomially related, which in other words means that there exists a constant C such that the block sensitivity is less or equal to the sensitivity power C. Okay, very good. So in that way, these both sensitivities are polynomially related. Okay, and this was the conjecture which was settled recently in 2019 and by Hao Huang. But wait, why are we studying this conjecture here? Why are we talking about this conjecture at all? Right? This is a course on algebraic graph theory. Okay, why we are dealing with sensitivity of Boolean function and the conjecture, the famous conjecture on theoretical computer science, what it has to do with algebraic graph theory? Okay, we will see that there is a very beautiful connection of this conjecture with some structure of a very beautiful kind of graph that we call hypercube graph. Okay, let us first define this hypercube graph and then we will see what is the relation of this sensitivity or this statement with the structure of hypercube graph, okay, or the property of hypercube graph. Okay, so let us first see what hypercube graph is. Okay, hypercube graph. Okay, very beautiful looking graph. Okay, this is a graph where vertex set is actually the set of all binary strings of length n. Okay, so vertex set is the set of all binary strings of length n. Okay, length n. So this is vertex set. So suppose this is called we will denote hypercube by this notation, okay, by n. Okay, so the vertex set of qn is this. Okay, vertex set is this. Okay, so how many elements will be there? How many elements will be? How many the band strings are possible of length? And there are 2 raised to the power n. Very good, very good. And then edge set of this is nothing but so very good. So I will define it like so. So any two vertices has an edge if the corresponding band strings differ at just one place. If the corresponding binary strings differ at exactly one place. Okay, so let us see some example of it. Okay, so what will be Q1, sorry, what will be Q1? Okay, on one length how many band string will be there? There will be 2, right? 0 and 1. Okay, and they differ at one way, so this will be this edge. Okay, this is. What about Q2? Okay, Q2 is about what? Okay, what about Q2? Okay, again, how many strings will be there? There will be 4 strings, so 0, 0, 0, 1, 1, 0, and 1, 1, and any 2 vertex will have an edge if they differ at exactly one place, right? So the corresponding band string differ at exactly one place. So this will be an edge, this will be an edge, this will be an edge, this will be an edge. Okay, on the diagonal there will be nothing. Okay, so very good. Very good. Now if you let us see what will be Q3. Q3 will look like this. It will, just check. Okay, there will be 8 vertices and the structure will be like this. Okay, in fact you can actually define Q1 in different way also. So Q1 is actually copy of 2 Qn minus 1. So there will be 2 Qn minus 1, and then you match every vertex. So ith vertex here will be matched with ith vertex, basically this edge, corresponding edges. Okay, so this is a matching, so 1 to 1 corresponding with each of the vertex here and vertex here. So this will be Qn. Okay, another way could be this one. Okay, so this we have already seen what we mean by Cartesian product of 2 graphs, right? So Q1 is nothing but what you do, you take K2. Okay, K2 is the complete graph on 2 vertices, and then do the Cartesian product n times. Okay, and then so this will be again will give you Qn. Okay, very beautiful structure. By the way, this is a bipartite graph. All the cycles here will be even. Okay, it's very easy to see. Okay, again a very simple DIY for you. Just check that Q1 is indeed a bipartite graph. Okay, very good. By the way, what about the eigenvalues of hypercube graph? We have seen that the eigenvalues of Cartesian product of 2 graphs can be actually derived from the eigenvalues of the individual graphs. Okay, so with the help of, we already know the eigenvalues of K2. What are the eigenvalues of K2? These are 1 and minus 1. Okay, it is very easy to see that the eigenvalues of K and Q1 are nothing but eigenvalues of Q and R are this. So these are nothing but n minus 2i. Okay, 2i with multiplicity n choose I. Okay, for I equal to 0, 1 up to n. This is DIY for you. Very simple stuff. Okay, very good. Okay, now about 5 minutes back I asked you this question: why we are studying sensitivity conjecture? Okay, sensitivity conjecture is actually related to hypercubes, a structure, a very nice structure, structural property of hypercube. Okay, and let us go to that relation between sensitivity conjecture and the structure of hypercube, and it was given by Gottsman and Lineal in 1992. Okay, so Gottsman and Lineal in 1992. Okay, so they have proven, basically they have established some connection between sensitivity and the structure of hypercube graphs. Okay, so but I will write down, I mean, the conclusion or equivalence that will be that will be relevant for us. Okay, that conclusion is this. Okay, the sensitivity conjecture is the sensitivity conjecture is equivalent to the following conjecture or statement, to the following conjecture, which is now theorem. Okay, following conjecture. Okay, so let H be a subgraph, induced subgraph. Okay, rather than I would say let be any arbitrary induced subgraph of Qn with the number of vertices in S is equal to 2 raised to the power minus 2 raised to the power n minus 1 plus 1, basically one more than the half of the number of vertices in Qn. Okay, then okay, the maximum degree which is denoted by delta H is at least square root of n. Okay, very good. So this is the actually the equivalence, the graph theoretical equivalence of sensitivity conjecture, which was given by these two scientists. Okay, which actually Hao Wang proved in very recently in 2019. Okay, and it made a very beautiful use of eigenvalues of some graph or some matrix which is very closely related to the adjacency matrix of Qn. But why not the adjacency matrix of Qn? Why we need to derive, or why need to introduce some another kind of matrix? Okay, just think about it. So we already know the relation between the largest eigenvalue and the largest degree of a graph, right? We know that the largest degree is actually the largest eigenvalue, but can the eigenvalues of Qn will help us? We have already listed down the eigenvalues of Qn. Okay, just check it. Why? But just looking at the eigenvalues of Qn will not prove this argument. We have to come up with some modification in the adjacency matrix of Qn. Okay, and then check the eigenvalues, and from there the result is very beautifully derived using Cauchy-Interlaced theorem. Okay, but I am stopping this lecture here. Okay, stay tuned for the beautiful proof of this conjecture in the next lecture. Okay, meanwhile keep on thinking. I hope you got the brief about the sensitivity conjecture. Okay, so see you in the next lecture.